Hello, AP Chemistry, and welcome to Chapter 4, Aqueous Reactions. So, we're going to talk about aqueous reactions. This whole chapter is just about different kinds of things that can happen in solution. It opens with what is a solution, really, really important, because a lot of what we're going to talk about this year goes back to particles, right? What do things look like at the particle level, right? Which means that it's really, really important that from the very beginning you can start to visualize our simplest concepts like solutions at the particle level, so that as things get bigger and as we basically just sort of add to our picture, right, that you can visualize what those particles are doing. Okay. Next up, we're going to talk about types of aqueous reactions, which is kind of a review from last year. Like, we talked generally about what an acid is, what a base is, and that they can react, right? Redox we didn't talk about last year, but it turns out redox is just like a broad classification for a huge set of reactions, which was beyond what we were going to talk about last year, but it's not very complicated really. And then titration is an application of both redox and acid-base concepts. Okay, so first of all, what is a solution? What is the act of dissolving, right? That's where solutions begin, right? In order to make a solution, obviously our solute must dissolve in our solvent, okay? Solute must dissolve in the solvent. Now, in order for the solute to dissolve in the solvent, huge, huge thing must happen. They must be able to interact, okay? They must be able to interact, kind of like they got to be able to hold hands, I guess. Whereas if we look here, right, at this picture, right, I think that it's kind of clear, right, in that if we look, this is an ionic compound, right, Na and Cl, composed of sodium ions and chloride ions, which when we dump sodium chloride in water, we all intuitively understand at this point that it dissociates into sodium ions, right, and chloride ions, right? We've been talking about that for a whole year. But what it means to dissociate into their ions, what it means to dissolve, right, is that it's being surrounded by water molecules, okay? Really, really important, by the way, if we look at these, right, water molecules, H2O, right, this part is obviously my O, right, and these are my H's. Yes? That makes sense. There's two of them. Okay. And what that means is in terms of my water molecule, right, so let's go up here and look at a little water molecule. So if we have a water, right, and we know that there are lone pairs here, right, this is the positive versus negative end of my water, okay? Whereas this end is technically our positive end, and this end, ooh, that's definitely not what I meant. This end is our negative end, okay? So it's like a little bar magnet, right? And each end interacts with whatever's appropriate, right? So if we look down here, sodium is a positive ion, so the negative end of water, a whole bunch of waters come and surround it, right, forming a hydration shell, okay? Chloride is negative, so the positive end of water surrounds it, forming a hydration shell, right? So what's really happening, right, is that the sodium chloride doesn't magically dissociate. What's happening is that each of the ions is interacting with the appropriate end of water so that it becomes surrounded by those water molecules, right? And that's how the sodium ions and the chloride ions hold hands and interact with the water molecules, right? Over here we have a different kind of molecule, methanol, which you don't really need to know too much about this yet, right? But methanol is able to interact with water via this part of its molecule, right? And if it didn't have that, it wouldn't be able to dissolve, right? Like oil is a hydrocarbon, has no oxygen atoms, and is unable to dissolve, right? Oxygen plays a huge part in a lot of how things behave. And we'll talk about that more later. But this picture, you should definitely understand and be able to render for yourself, right? This one is a little bit more complicated, and we'll do a lot more work with that in a couple of chapters. Okay, so for over here, we're looking at a couple of different types of compounds, right? KClO3 versus this versus that. What do we know about KClO3? Right, it is an ionic compound. So, for starters, let's talk about what it does in water. Right, we understand that it breaks into K plus ions and ClO3 ions. And that's what ends up in our water. Now, if we were going to go one step further, right now we should be able to talk about the fact that my K plus ions find themselves being surrounded by the negative end of water. Yes, right? Or if we want to draw it as like a little dot structure or a little, I don't know what they're called. Particle diagrams, right? We could have our oxygen and our 2 little hydrogens. Okay, but the point is, right, whereas these would be purple, I guess, and the oxygen would be black, right, showing that the oxygen end is preferentially interacting with the potassium, right? Likewise over here, it would be the opposite, right? Whereas that end would be interacting there, or we could say that the hydrogen end, yeah, I don't know how I meant for that to look. I think that's what I meant. The hydrogen end is interacting over here, okay? And then likewise, we could repeat that with this, bearing in mind that we get lithium ions and chloride ions. What happens over here? Right, no ionization because it's not an ionic compound. It's not composed of a metal and a nonmetal or polyatomic ions, right? Now, some of you might be like, oh, well, isn't this a polyatomic ion? OH does serve as a polyatomic ion. Turns out OH also serves as a functional group when attached to a hydrocarbon, okay? Which is what we have here. This is not a metal, this is a hydrocarbon. Hydrocarbon, yes? So, this is not an ionic compound, meaning it does not dissociate into ions, right? If we just think really, really briefly about what it kind of looks like, right? There's C and our H's, C, H, H, right? So this is this, right? So it's written kind of the way that it looks, right? And a lot of organic compounds are purposely written that way. So you can see it, right, in the formula, right? And over here, we do have an O and an H, right? And this is sort of the same idea, right, where it's kind of like a water, right? And this is what allows it to interact with other water molecules. We're going to get more specific about those details, like I said, in a couple chapters. Okay, next up. Micro versus macro, really, really important, like I talked about already, right? It's important that when you look at this, right, if I say that that's aqueous sodium potassium iodide and this one is aqueous lead nitrate, right, it's important that you should be able to tell me, right, that this is potassium ions and iodide ions, lead ions, and nitrate ions, right? And then what happens when we mix them together, right? And this is why, again, if I just took solid of these two and mix them together, nothing would happen, right? Because they have to be separated so that way they can run into each other, the respective ions can run into each other, and we can get chemical reactions that happen. So here, when we see the formation of the solid, we understand that that is what happens when lead ions run into iodide ions, and they form lead iodide, which is not soluble in water, right? And so if we were going to draw a particulate diagram over here, right, these would be lead and iodide ions literally stuck together because they're not ionized. And up here, right, they would still be free floating ions of the excess reactant and whatever other thing, and our spectator ions would all be floating around up here. Excess and spectators would all be floating around, and my solid would be here, and we would depict them as being stuck together. By the way, this is the same idea as one of those things that was on your guys' AP pretest, right? So if this kind of rings a bell and you remember yours being particularly bad, right, spend some time looking at this a little bit longer. Okay, quickly, net ionic equations, really, really important, right? This is one of the silliest things to lose points for on the AP exam. All you have to do is like pay attention, I guess, right? And know your solubility rules, that helps also, right? So let's go ahead and do this example really quickly. So we want the net ionic of silver nitrate and potassium phosphate, and it says that they are aqueous solutions to begin. So we will take our AgNO3 aqueous plus potassium phosphate, which is KPO4 aqueous, and we know that this is what kind of a reaction? Ding, 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 double displacement. KNO3 plus AgPO4, 3. Okay, now let's get some states on these. Right. Always soluble for both of those. Here, definitely a solid. So then we'd go back and we would balance accordingly, right? We go put a 3 out here and a 3 over here, and we would be done. So this is our complete equation, or our molecular equation, even though they're not molecular compounds, but that's what it's called. And then we would whittle this down to our net ions, right? All of these, so for everything that's aqueous, that means it's going to dissociate into ions. So that means that we have 3 Ag ions, right? We have 3 nitrate ions. We have 3 potassium ions. We have 1 phosphate ion. We have 3 potassium ions. And 3 of these. This is very tedious. But hopefully the point is that, oh, and then we have, oh, nope. And this stays stuck together, right? Stuck together because it is not both aqueous and soluble, right? Or soluble and ionic. Then we cross out the things that cross out on both sides. So we'd go through here, and looks like the nitrates cancel. I forgot to write the negative there, but they do cancel. Potassiums cancel, and everything else becomes my net ionic. And when you're asked to provide a net ionic, right, all of this needs to be there. If you're missing any of these components, it's not going to be correct. Right? So if you don't put these charges, it's wrong. If you don't put the aqueous, it's wrong. If you don't put the right stoichiometric relationships, it's wrong. Right? So please think about those things. And if we go back up here, right, this green step really, once you're really comfortable with your solubility rules, shouldn't be an issue, right? Because we know if this is aqueous, oh, we have silver and we have nitrate ions. We have potassium and we have phosphate ions, right? Potassium and nitrate. And you see, oh, these are the only ions that change, are silver and phosphate. So we go pick out our silver and pick out our phosphate and make our compound. In my head, that's what I imagine happens anyway. Okay. Thank you for listening, and we pick up in the next one with a little bit about acids and bases. See you soon. Be good. Bye.